This is characterizing 5G leakage passive weather sensing spectrum bands. Official name. My name is Noam Hirschorn. I was advised by Professor Ivan Siskar, Professor Narayan Mandayan. Okay, so basically, let me explain what that title means. First, get into background. So everyone's probably heard of 5G is coming. And so one of the things about 5G is that it's going to be able to send a whole lot more information than we've been able to in the past. Thing is, though, that you can, in order to send information, it's something called the electromagnetic spectrum, right? That's just how all information is sent wirelessly. And so since we're going to need to send a lot more information, we're going to need to use a lot more of that spectrum than we have been using, including something called millimeter wave frequencies. It's above 20 gigahertz on the electromagnetic spectrum. However, the issue is that there is currently weather sensing, passive weather sensors, which are centered at 23.8 gigahertz. And so if you were sending all this information around that frequency from 5G, then we're worried it might interfere. So we want to determine exactly how much that could be, like how much of an issue this is. So here's a nice little graphic showing how they can interfere. Yeah. So the objective, a formal objective, is to figure out how much unwanted leakage, so basically interference generated by 5G signals in millimeter wave frequencies, and we want to quantify the potential impact on weather sensing. So I'm going to go into a bit of background. So basically, when I want to send a signal, I want to send information, there's a range of frequencies which is ideally sent over. And so, and actually everyone who's sending signals, like all these like Verizon and all these different companies, they each have these spectrum licenses in the US by the FCC, and they buy them, and therefore they are the ones who are allowed to transmit over that range of frequencies. And ideally, they would basically just use, let's say they bought from A to B, frequencies A to B, so then they would just use it, and it would be a nice little rectangle. And then that rectangle, all the information, all the data would just be sent over there. And that's called a bandwidth. So just between the width of each of these rectangles. However, we don't live in an ideal world. Like the signals aren't actually shaped like rectangles. They're actually shaped like waves. You can see the picture there. And the bandwidths of these waves are generally wider than is ideal. If we ideally could fit all this information in a rectangle, it would be narrower and be better. And so what we do now is just you buy a little larger band spectrum, then you're actually going to send information, because the ends of it basically have to just account for the wave just going down. However, as you go up frequency, as we're trying to go to above 20 gigahertz, these coattails, or whatever you want to call it, might get wider, which cause more interference. And so, kind of like what I was saying, so let's say these two blue lines are the intended bandwidth, right? So that's what we want to send in. But then outside of it, you still have these coattails, whatever, and we call that leakage. So that could be the potential interference. And so in the study, we're going to use something called the negative 3 dB point. It's one of the ways of characterizing, okay, where is the intended bandwidth versus where is leakage? It's actually, I'll go into a bit later, but that's one of the long-term issues with the study, is trying to figure out exactly where to draw the line. And also you have this thing called the noise floor, which is basically just sonoric calculated leakage, just calculate the amount of area that is above the noise floor, which is just the base level on the electromagnetic spectrum. It's like in this constant low level frequencies sorting up and down, very low level. So you just calculate, and it's the leakage, just calculating how much area above that is caused by the signal. However, the other issue, in addition to calculating what the intended bandwidth is that the noise floor isn't so flat. Like this is a picture I just took of the noise floor. So where exactly do you call, the line, which, okay, everything above this, I'm going to call leakage. I'm going to call, I should measure the leakage of the signal, interference of the signal. So that was the other, I'll go into how it is specifically in each experiment, but that was the other longer term issue just with each study. Okay, how am I going to do? Those are always the two things. Okay, how am I going to characterize the intended bandwidth, and how am I going to figure out what the noise floor is? A bit of background. So the first experiment I did for a few weeks in, I was setting a signal at 5 gigahertz. That's much easier to deal with. And I would also vary the sampling rate. So that basically is how much information is sent per second. So more information sent per second, as you can see, it definitely has an effect on the amount of leakage, which I won't spoil it. And the other thing I was testing was increasing the gain. So the gain is just the raw power. And again, the sampling rate is just the amount of information given per second. And this one on the left there, you can see the basic layout for how it looks. So key things I want to point out is that it's a wired transmission, and I'm using a spectrum analyzer. And that was helpful, especially for experiment 1, in order to do things. So this is on the right. That's an example of a wave, and I won't go into it. And the green is what I measured to be leakage. And if you notice, and since it's a wired transmission and it's a spectrum analyzer, which is a special tool, which among its features can help lower the amount of noise floor, you can see the wave and even the actual noise floor. See, it's actually relatively it's not completely flat, but it's pretty close. And so it was relatively easy to figure out the noise floor. I think I got the first and last 4% of the waveform. I just called that the noise floor. And then you can see where I did it by where the green lines end. Because the green line is the leakage, then I just calculated up the total area. And this was my results for a subset of my results, at least. You can see there's 3 lines here showing the gains and also the sampling rates from 1 to 10 megahertz. And you can see as you increase the sampling rate, you are increasing the amount of leakage. And the thing is, I went through 10. When we get to, this is only 5 gigahertz. We get to in terms of the sampling rate. So it's really gonna add up. And yeah, you can see the relative flatness like I mentioned. And meanwhile, I want to track that to experiment 2. So this is an experiment. It was also at 5G, but in this case, I actually transmitted it over the air as opposed to over a wire. Also, I did not use a spectrum analyzer. I instead just got the raw data. And so this, I will show you soon, it was much noisier. So I actually literally just did a whole bunch of runs of just pure noise just in order to try to figure out what the noise floor was. Because I would just find the average for 16 runs of noise, where I didn't send any signals. I just got what the electromagnetic spectrum looked like at that place. I just figured out what the noise floor was there, as opposed to just getting the first and last 4% of the waveform. Because, because if you look at it, where's the noise floor here? This is a wave. And so it's much messier. So I couldn't just take the first and last 4% and just call that the noise floor. So I instead had to do a whole bunch of just pure noise runs. And you see it's much noisier overall because it's over the air. So all the over the air interference, all the interference just from the outside world. And also I'm not mitigating it a bit with spectrum analyzer, it's just the raw data. So this is me after some analysis. So the blue is a nice envelope, and that's in order to calculate the -3 dB point. Where's that? Where it looks a bit different just because the way it works, the point is where's the intended bandwidth. So I use that envelope in order to find it. In blue, and the green is just the excess area of the red wave. If you notice, I actually am just going all the way from the intended bandwidth all the way out. That is including some noise. However, I then just subtracted the area from the noise. So basically, I would find the noise floor. I would take the area from the wave with the transmission. I'd subtract the area from the wave without a transmission in order to get what's the leakage. And you can see this is my results. So it was much higher variance. Those bars represent the 90% margin of error. But you can see there still is a definite increase as you increase the sampling rate or bandwidth. Confusingly, it's 2 names for it. Basically, as you increase the sampling rate, you can see the amount of leakage is going up. And so that can be very worrying as we're increasing it by a lot more than this in order to get to millimeter wave. And so the current steps, actually, literally, I was just doing this yesterday, was that I was starting to send signals at between 26 and 28 gigahertz with 100, and it was doing 125 megahertz, which is about what it's going to be using. And Then once I have this data more formalized, a whole bunch more measurements of it, the next steps are we can actually talk to weather researchers to determine, okay, how much leakage is enough to throw off their equipment. And then we can go from there. We can't get exactly to 24 gigahertz just based on the current hardware that we have, but we can extrapolate from, let's say, 26 gigahertz to see, okay, how close can we get to a certain frequency before the leakage will be too much. That is, basically the longer term point of the project in order to avoid 5G from interfering. And for more details about the process, especially for analyzing the waveforms, I glossed over it a bit in terms of how my MATLAB code exactly worked. So you can see the associated papers on my website. Link is right there. And thank you. And, have a good day. Any questions?